Hi, everybody. My name is Laurie Voss. I am Head of Developer Experience at Arize AI. In a former life, I co-founded NPM Inc., so some of you may remember me from when I used to talk incessantly about JavaScript. Now I talk incessantly about AI. What I think about mostly is how to test AI systems, how to make AI systems that actually work. So we've got a good long stretch of time today, so we're going to cover a lot of ground. We're going to start with the fundamentals, what evals are, why you need them, and why agents make evaluation harder than a simple LLM call is. And then we're going to set up tracing, which is how you capture the raw data that you need to run evals in the first place. We're also going to run a simple AI agent with the Claude Agent SDK and look at the traces that it produces. Once we've looked at the data, we're going to do something that most of the tutorials skip. We're going to actually look at the data. We're going to read our traces, categorize what went wrong, and figure out what to measure before we write a single eval. Then we're going to write three kinds of evals. We're going to write a simple code eval, deterministic, cheap, easy to run. We're going to use some of Arize's built-in evals. And then we're going to use LLM evals, where an LLM judges the semantic content of the output and judges whether things have succeeded or failed in a more flexible, non-deterministic way. We're going to use the built-in evals, and we're also going to write a custom eval from scratch. And we'll also test whether our judges are judging correctly, a process called meta-evaluation. And then we'll finish with data sets and experiments. This is how you iterate on your agent. This is how you use evals not just to tell you whether things went wrong, but to improve your agent. And we're going to do, at the end, a brief look at what comes next after you've got this stuff down. So practical frameworks you can use after you leave this room, the impact hierarchy, the data flywheel, and a quick tour of techniques like pairwise evaluation and reliability scoring. This is the slide that I left up while you were waiting. Hands up if you intend to actually attempt to code along. Wow, impressive. Also, just impressive how many people are in this room. Like, this is the last session of the day, and it's evals, kids. Do you know that it's about evals? This is like, it's not the most exciting topic. I'm very proud you're here. This workshop is about evaluating an agent, though, so it's not going to be about building an agent. I'm kind of assuming you've already built an agent and you're having problems with it going off the rails radically. So the learner notebook that you're going to get there has an agent already built for you. We are not going to spend any time on how do you build an agent and what makes an agent good or bad. We're going to be evaluating this agent that I've already written. We're also going to be using Claude both to power the agent and to power the evals. I picked Claude because everybody seems to have switched to Claude in the last couple of months. Like, I'm hoping you have a Claude account already, so you don't have to sign up for an API key right now. But if you do, now is the time. You can, if you want to, use OpenAI or Gemini with our stuff. It is completely open source. It is open standards. It will work with those as well. But for simplicity, I have not included any examples of how to use OpenAI or Gemini in this stuff. You will also need a free Phoenix Cloud account. Phoenix is open source and will run on your laptop, but Phoenix Cloud doesn't involve installing anything, so it's the easier way to get up and running faster. Phoenix Cloud is where our log data will be sent, so you'll need a Phoenix API key to get permission to send it there. Hopefully you've got these links to these slides, because I'm going to advance them in a second. And really, you only need the one to the notebook, because the notebook has the links to everything else in it. Who is, at this point, completely confused and needs some help? Because I've built in some time for that. Feel free to ask questions, and don't worry about it. I've built in time for asking, like, I don't know what this is. I'm accidentally on the wrong product. Speaking of which, Arize has two products. One is called Arize AX, and one is called Arize Phoenix. We are working with Arize Phoenix today. If you go to our homepage, there's a big button on it that says sign up, and it will sign you up for AX, which is the enterprise product. And you don't want to do that if you're completely confused about where your API key goes and what your host name might be. It is because you've signed up for the wrong product. So make sure you are signing up for Phoenix. So with that stuff out of the way, or at least while you're frantically still installing things, let us cover the basics. What is an eval? Who in the room, show of hands, feels like they already know what an eval is? Like really knows. Okay, great, you're in the right room. So one of the things that bugs me about evals as a field is that we use a whole bunch of words that come from ML land. We use a bunch of jargon that comes from ML land that AI engineers do not need to know and do not understand, and makes it needlessly opaque. So you can think of traces, you can think of evals as being tests, because that is what they are. And the things that power our tests are log data, and the log data we call traces. So just as logs record what your server did at runtime, traces record what your AI did. Every agent call, every tool call, every LLM invocation, all of the inputs and outputs from your AI application are recorded as traces. And the building blocks of traces are called spans. Each span represents one step in the execution. So an LLM call is a span, a tool call is a span, a full agent turn is a span that contains other spans inside of it. It's this nested data structure that can be easily imagined as JSON, because it is JSON a lot of the time. Each span records its input, its output, but also a bunch of metadata, so things like timing and token counts, stuff that you need to understand what went on. And that is your mental model today. You are writing tests for a brave new world of applications that are very hard to test. So it's not rocket science. Why do we need them? Well, the reason we need AI evals is because of the vibes problem. A lot of people build an AI feature and test it by running a few queries and sort of going, does this look right? Then you ship it, and it fails on inputs that you didn't test. It fails on edge cases. It fails on people being adversarial and putting bad stuff in there that you weren't expecting. And it fails most often on people asking questions that are dumber than you were expecting. That is the primary way that agents fail, is people using vocabulary that you weren't expecting to hit an agent that is expecting a bunch of nouns and verbs that those people don't know. So the usual fix unit test doesn't work here. And the reason that's true is because the same prompt will produce different text on every single run, but those outputs, those different outputs, might all be correct. There's a huge space of potential correct outputs, so you can't just have basic string matching like most unit tests do to make sure that your tests are running successfully. So a lot of teams fall back on human review. They watch it, they run it, they ship it, and that doesn't scale because it doesn't catch regressions, and most importantly, it doesn't run in CI. So what you can't do without evals is you can't change your system prompt to fix a tone issue, because the tone might get better, but suddenly the bot might be hallucinating product features, and without evals, you won't catch that. Without evals, you won't catch that because until a user reports it. But you can do something called a faithfulness eval, which will tell you whether or not your bot is actively using its source material correctly. And we're going to show you how to build one of those today. And every prompt change potentially affects every kind of input that users send. This is another way in which AI agents are different, is if you change one thing about your prompt, it doesn't just change the thing you were trying to change. It changes everything that the agent does, because the agent absorbs the prompt as a block and will do unpredictable things as you make even minor changes in wording. So you don't want to fix one thing and break another. And evals give you a way to test that everything is working the way that it is supposed to, including all of the things that it used to do. You also can't switch models without evals, and this is very important because the big model labs come out with a new model every couple of months. And the models are meaningfully different in how they're not just better, they're different. So a prompt that worked for Sonnet 4.5 does not work for Sonnet 4.6. And if you don't have evals, then that's a very expensive and cumbersome process where you have to test everything that you tested previously again to see if it works. Whereas if you have a suite of evals, you can just run a regression and know whether or not it is safe to upgrade. And this is not theoretical. Real teams that are shipping real AI agents that people use all the time, Descript, Bolt, Anthropic itself with Claude Code, this is how they do it. They all followed the same pattern. They started by shipping fast and checking things with vibes and discovered that it didn't scale and moved on to formal evals. So that's the arc that we're going to follow today. Like I mentioned, there are two types of evals. There are code evals, which are deterministic functions you write yourself. They're just basic Python or TypeScript. They run in milliseconds, and because they are just code, they cost basically nothing to run. You can do a lot with code evals. If the output of your agent is supposed to be JSON, you can test whether it is JSON. You can test whether it is under 500 tokens. You can check whether it mentions the thing that you asked about. The big advantage of code evals is that they're super fast and super cheap and totally reproducible. So if you have something simple that you need to test, you don't need to throw an LLM eval at it every single time. You can get quite far with things that look basically like old-style unit tests, although there is a lot of subtlety to how to put them together that we're going to cover today. The downside of code evals is that, like unit tests, they're going to be brittle. When your output becomes complex or extremely non-deterministic, you're going to find that you need to move to the other type of evals, which is LLM-as-a-judge. With LLM-as-a-judge, you use a second LLM to judge the output of the first LLM. Usually you use an LLM that is more powerful than the one that you put into production. You grade your outputs against a rubric, rubric being another one of those terms that the ML engineers snuck in there. A rubric is just a set of rules. It's just a prompt, basically, that defines all of the things that you need to test. And because LLM evals are powered by an LLM, they are a lot more flexible. So you can say, was this response factually accurate? You can say, did it stay faithful to the source material? You can ask, is the tone right for a customer interaction? There's no kind of unit test that you could write that would check for tone, but an LLM is very good at that kind of stuff. The strength of LLM judges is they understand meaning, not just basic strings. But LLM as a judge has trade-offs. The biggest weakness is that they are expensive, both in terms of time and actual money. And they are non-deterministic themselves, which means that your LLM as a judge can itself be wrong. You have to prompt your LLM to be a judge, and that prompt is just as complicated as the prompt that you were putting into your application itself. So you have to spend some time making sure that your LLM as a judge is aligned, that your LLM as a judge is actually judging what you intended it to judge, and that it does that in a way that you believe is correct. There's also a third type of eval, which is human evaluation. Human evaluation is the gold standard. It is great. Humans are the best at judging whether things are good or bad according to other humans. The problem is that humans don't scale. You need this stuff to run in CI. You need it to run thousands of times a day. There is no way, even if you work at Meta or Google and you can hire the population of a small country to do your evals for you, that it's going to be cost effective to have humans doing your evals for you. What we use humans to do is to build what we call, you're going to hear about this later, a golden data set of known good answers that you can then judge your evals against. A fun fact about human annotators is that about 50% of the time, even if you are using humans to judge the output of your AI application, they're going to get it wrong 50% of the time, because if you hire somebody to do nothing but test your code, they're going to get tired. Just fatigue makes them miss things roughly 50% of the time. But code evals, human evals, and LLM as a judge, they are not competing approaches, they are complementary approaches. A real eval suite is going to use all three of these at the same time. So the question becomes, when do you use which? Use code evals when the answer is deterministic. So format validation, length limits, forbidden phrases, required fields, all of that kind of stuff you can very deterministically check. And then use LLM judges when you need semantic understanding. So like I said, a correctness eval asks, did it answer the question accurately? A faithfulness eval asks, did it stick to its source material and only its source material when you were answering that question? And you have to keep humans in the loop for failure modes you haven't seen before. You have to make sure that your evals are being run in a way that humans believe is real and believe is correct, because LLM judges can be wrong. And all of that stuff is true of any application that uses an LLM for anything, but agents make it even harder because agents have cascading failures. And in an agent, you have not just one thing that you are testing, but a series of things. You have an agent that can take any number of paths, and an early misstep on one of those paths can lead the agent to radically incorrect directions. So if you imagine asking if you have an eval that has, if you have an agent is making tool calls, you have to test whether the agent picked the right tool, whether it sent the right parameters to that tool, whether it correctly understood the output of that tool, and that's just adding one tool call, whereas an agent can run multiple tool calls in a single session. And each of those tool calls relies on the output of the previous tool call. So it gets very, very complicated very, very quickly, which is why you generally need to throw an LLM at the problem. And then there's multi-agent systems. If you haven't made things complicated enough, you get additional levels of complexity, because then you have to test, did my routing LLM choose the right sub-agent before anything started happening? And then did my sub-agent correctly understand what it was being asked to do? Did it pass the information back correctly? Did it stop when it was supposed to? So all of this stuff builds up in cascades. An example would be, you ask your agent to write a report on Tesla. The first agent that does the research is like, oh, I guess you must mean Nikola Tesla. It sends you a whole bunch of information about the 18th century inventor, and then you output an investment case that is based entirely on whether Nikola Tesla was a good guy, and that gets forwarded to your boss. And nobody notices because the agent was just doing this all autonomously. That is the cascading failure that we are trying to avoid. But agents can also do the opposite. They can get things right in a way that you weren't expecting. So one of the hazards of writing evals is writing evals that are too prescriptive. You don't want to write an eval that says, I'm expecting it to call tool A and then tool B and then make decision C and then get the answer, because the agent might find a way to be more clever than that. This happens a lot in production. The agent will find a loophole, or it will find a faster way of doing what it's doing, especially if you've just upgraded your model. It will get better at doing things that it was doing before. It will do them in fewer steps, so your evals will break if they are too prescriptive. Yeah, and that's a hard problem. There's another way to categorize evals into two groups, which is capability evals versus regression evals. So a capability eval is giving your agent a hill to climb. You've given it something that you know that it's bad at, and something that it's going to mostly fail at. And you are giving it a loop where it can get progressively better at passing this capability eval. Once it's hit 100% on a capability eval becomes a regression eval. You build that into your test suite, and you make sure that it can always do the things that it used to be able to do, and you give it a new capability eval where it climbs a new hill and adds a new functionality. So in the life of your eval suite, you're going to be constantly turning capability evals into regression evals. This is what an eval result looks like. It's very simple. You can imagine a JSON object with this stuff in it, because that's what it is. You get a score, a label that is human readable, and LLM judges add a third thing. They add an explanation. Code evals don't produce explanations because they are just code. You didn't build an explanation into it. But LLM evals are extremely helpful in that they don't just say that something was wrong. They say why they think it was wrong. As we're going to see, this is extremely helpful when you are building your eval suite. Because it can tell you what was wrong, it can tell you what was missing, it can tell you what the agent should have done differently. It will give you hints as to how to make your prompt better, which is extremely helpful. Here's what an explanation from a real eval looks like. So in this case, the prompt was the user was asking for budget travel recommendations for Tokyo. And the LLM-as-a-judge has said, OK, well, they gave travel recommendations, but they didn't specify how much everything cost. So if I'm looking at budget travel, that's a failure. That's a really subtle distinction, right? Because if you were saying, did it give me travel recommendations to Tokyo? It absolutely did. But it didn't follow everything I asked it to do. It didn't follow the subtlety of the original request. And that explanation is what makes evals actionable. You know what to fix in the prompt because you have an explanation that says this is what went wrong. And more usefully, when you run evals across thousands of traces or thousands of spans, you will find patterns. You will find that your agent fails on the same kind of problem in the same kind of way lots and lots of times, and that gives you a hint as to what is a one-off failure, just the agent being weird and non-deterministic, versus what is a systematic failure, which is likely to be a problem with your prompt. Of course, if you've run an eval against 1,000 traces, and you've got 1,000 explanations, then you as a human have to read 1,000 explanations, which creates a new problem, which is reading 1,000 explanations and categorizing them all is kind of a pain in the ass. So you get a third LLM involved, and you get the LLM to read the explanations and turn them into categories until it's LLMs all the way down. So this is the full loop that we're going to build. Instrumentation is where you start. That is where you start capturing the data. You get traces, you evaluate them, you annotate your evaluations, you analyze the results, and then you change your prompt, you change your application, you improve your application, and you start over. So let's get started with the actual evals. Who wants to be set up with Phoenix is not yet set up with Phoenix? OK. What do you need? Where are you stuck? Or are you not? OK, sorry. Great. Excellent. Everyone is set up with Phoenix, as far as I can tell, or they're not brave enough to put their hand up and say they aren't. So what is Phoenix? Now that I've been talking about it for 20 minutes, Phoenix is Arize's open source AI observability platform. What it does is it captures your trace data. It captures those logs that we're generating. So every LLM call, every tool call, every agent step, with the inputs and outputs at each point. And it also captures and stores your evals and gives you a UI for examining all of that. And it also gives you a way to run experiments on that data so that you can test how things are improving and make your application better. Like I said earlier, you can run it locally on your laptop if you want to, but we're using Phoenix Cloud today because that involves not installing any software. So let's look at our actual notebook. The first thing is the pip install. We're installing the Claude Agent SDK. Like I said, we are installing Open Inference Instrumentation Claude Agent SDK. This is the magic. Every SDK, every framework that is out there has a integration package written by us that automatically instruments and starts collecting logs from that framework. This is why Arize Phoenix is so useful, is you don't have to dig into the bowels of your framework or dig into the bowels of OpenAI or Claude or Gemini and get it to send logs to you. The people who built that software have already decided on this open source standard called Open Inference, and they've plumbed in all of those log lines already. So all you have to do is tell it to start sending those logs to a particular place. And that is what we're going to do in a bit. So let's move on to the very first call. We've got those API keys. My API keys were pulled in via Colab secrets, but you can just paste them in because no one's going to see your screen, right? There's only you in this room. And then these two lines of code are the magic. You import phoenix.otel and you call register. You give it a project name. That's how you know what name it's going to show up in inside of Phoenix. And you tell it auto instrument equals true, and that is the magic command that tells it dig into the internals where you already know how to do stuff and turn on all of the logging. It's complaining at me in this error message because it is using a span processor, which is good for demos, but not good for production. In production, you're going to get thousands of spans at once, so you want to use a batch processor. But this is not that, so it doesn't matter in this particular instance. Oh, yes, we also brought in Anthropic up in the imports because we're using Anthropic to do the actual to be the LLM that runs the LLM-as-a-judge, which is why we have to bring it in separately to the Agent SDK. The Claude Agent SDK, if you haven't used it, is a very, very simple framework for building agents. That is why I picked it, because it's nice and simple and it doesn't have a whole bunch of ceremony. The agents can use tools, they can search the web, they can maintain conversation across turns, which is really all I need my agent to be able to do for the purposes of this example. OpenAI has their own agent SDK, and of course there are whole agent frameworks like CrewAI, LangChain, Master, Llama Index, all those sorts of things that will let you build a lot more elaborate agents. And we have instrumentation packages for all of them. So whatever you have used to build your agent, you can do the same 2 lines of code and just turn it on. You can go ahead and run that call.
Sorry, may I ask a question?
Sure.
The Phoenix app, I go to setting, I get the Phoenix cloud, Arize, and I cannot find where to generate the API key. Am I right?
Oh, no,
Go to
happened to me.
go to spaces.
You gotta initialize one space before.
So I have to select the
Yeah,
space.
you gotta launch.
Just launch the space, and that's what you want.
Thank you.
Great.
I have a question, actually.
Sure.
What's the Phoenix collector endpoint?
The Phoenix collector endpoint is the thing that I called the host name.
So
It's app.phoenix/s/your username. All right. Anybody else need help on that kind of stuff? Cool. It is warm in here. So let's look at the actual agent. Today we are building a financial analysis agent, a very, very simple agent indeed. It has just 2 sub-agents. It has one agent that does research. If you give it a stock ticker or a set of stock tickers, it's going to search the web for information about those companies. And then it passes that information to the second part of the agent, which writes a concise financial report about that research. Obviously, a real financial research agent, which is a thing people build in production all the time, is going to have a lot more elaborate databases to refer to. It's going to have it's not just going to be doing web search. And it's also going to be able to write much more complicated reports. But that is fundamentally what we're going to ask it to do. And here is how the 2 turns connect. You can see the Claude Agent SDK maintains conversation context. So turn 1, it's doing research. Turn 2, it's writing a report. And because they are both using, in this line, the Claude SDK client, the context from the first one is shared to the second one, and that's all you really need to know about what this agent is doing. I'm not going to go into the details of the boilerplate there that is just handling output. So next you set your API keys. Like I said, you did all of that stuff already. You've done your register step. I want to emphasize again, if there's anybody in the room using Phoenix AX, you are in the wrong place. You should be, using Arize AX, you should be using Arize Phoenix. But I think everyone's got that down now.
It redirects you from one to the other.
Oh, really? Oh. Yes. So we showed the register function already. The register function sets up OpenTelemetry. OpenTelemetry, also called OTel, is used by all of the major observability providers. So anybody who's doing logging, Kubernetes logs, all that kind of stuff is done via OTel. There is a layer on top of OTel called Open Inference, which adds a lot of extensions to OTel that are LLM specific. So stuff like prompt text, completion text, token counts, which model was called, what tools were invoked, all of that kind of stuff is handled by the Open Inference extension to OTel that everybody builds for. And now we're building our agent. Like I said, those 2 steps. This part is just us setting up our agent. We're using Claude Haiku. The reason we are using Claude Haiku is because it is reliably dumb. It's not a very good agent, so it's going to make some mistakes, which will then give me something to test against. And I've given it one allowed tool, which is web search, and I've also given it a permission mode of accept edits, because otherwise it kept trying to prompt me to like be able to change files, which turned out to be a mistake that we're going to cover later. So it's cheap and fast, and it's great for demos like this. And these are our two turns, research and write report. And we wrap all of this in an async function called financial report, which is all we need to create an agent. We also do this line here, which is we are wrapping all of it in an OpenTelemetry span. The reason we are doing that is because by default, the step 1 and the step 2, the research step and the write report step, will show up in Phoenix as separate traces because they are separate agent turns. So we are here telling the agent that both of these should be considered a single agent doing a single thing. So we're just sort of pre-formatting our data to make it easy to handle the agent. And with that done, we can run our agent. If you run your agent now, it will take a minute or two. You can give it your own stock ticker and your own focus area if you want. I've given it Tesla. And this is what it wrote for me. It output some boilerplate about what it was doing. It was researching, it was writing, and then it gave me an executive summary about Tesla. So we're asking it specifically to analyze the financial performance and growth outlook of Tesla. And you can see that the LLM does multiple rounds of reasoning at the top. It does multiple steps of research before it gets to the writing stage. What's happening under the hood is it's doing a series of web searches. It's doing a web search. It's finding out whether or not those search queries gave it useful information. It does more web searches. It goes into further depth. It is doing what an agent does. It is being non-deterministically helpful. And that is important because we couldn't have written a test that said it does one web search and it gets all the answers. We couldn't have done a test that said it did 5 web searches and got an answer because we simply don't know what it's going to do. So then when it's done researching, we send the writing prompts and it compiles everything into a report. And all of this stuff is non-deterministic, and that's cool. And that is why we need evals, like I said, because we can't predict the output from the input alone, and every single one of those decisions is going to be captured as a trace that we can test. So this is what it produced. Q4 25 highlights, 2026 financial outlook, key growth drivers, risk assessment, fantastic. It looks pretty legit to me. But pretty legit is not enough to ship something to production. That is the whole point of evals, is that the vibe is good, but we want to be doing better than vibes. So let's see what Phoenix captured when I ran that agent. This is what the Phoenix UI looks like. Each one of these rows is a span. So at the top level, you're seeing the input and output of the entire agent span. That was that thing that we did that wrapper around. You're seeing that it said research Tesla and focus on financial performance and growth outlook, and you're getting the same output that we showed in the collab. But inside of it, you can see all of the things that went into it. So you can see in this instance, it did 4 different web searches. It queried financial performance. It queried growth outlook 2026 future. It queried quarterly results, revenue, profit margins. And it queried Cybertruck production roadster demand 2026, which I feel is particularly ominous for Tesla in 2026. And you can see the 2 steps, one where it did the research, and you can do the other step where it did the output. So all of the steps, every single thing that your agent did is captured in the Phoenix UI. And that is the key to observability. We can observe. We can see what the hell is going on. That is what we wanted to be able to do. Traces reveal every decision the agent made. And you can click into any span and see exactly what the model received as output, like I said, and all of that stuff. Let's switch back to slides. What lives in a span? We've got a whole bunch of stuff. If you click into a span itself, you can get the exact details of a span, so you can see annotations, attributes. Like I said, there's a lot of JSON under the hood. This is an actual span. This is, you can see there's cost in there, there's what model it was using, there's the token count, how many things it went through, and then the output messages is giant blocks and a whole bunch of other stuff. So what Phoenix is doing for you here is making this stuff a lot more readable than it would be by default. But just one span, just one agent run is not enough. We want to be able to have multiple spans. We want to have a whole bunch of data to know what's going on. So in the notebook, there are 12 test queries that you can run. It just takes a whole bunch of tickers and a whole bunch of focus areas, and it runs them in a loop and runs the agent 12 times. I've already run these ahead of time because it takes a long time to do that, but you should kick them off now, and while I'm talking, they will run in the background for you. It should take about 5 minutes, but timing on this stuff is tricky. That is why I picked Haiku as well, because it's fast, because it's not thinking very hard. And while we're doing that, we can go back to our slides and cover some theory. So we've got single ticker analyses, different focus areas, financial performance, revenue growth, competitive landscape, AI strategy, and one comparative analysis where I've asked it about 2 tickers at once. I've asked it about Apple and Microsoft and told it to compare the 2. This gives us the variety that we need. This is important to test a variety of possible use cases for this agent and how it would behave in those cases. In real data, you would not just have 12 of them, you would have several hundred of them based on all of the things you're expecting people to use this agent to do. And it's very important to cover the edge cases. The Apple-Microsoft comparative analysis, for instance, is a lot harder than a single ticker query because it has to do 2 sets of research about 2 different companies and not get them confused, and then write a report about both of them at the same time. The Rivian query, for instance, asks about a company that isn't public yet, so there's much less obvious data sources for where it can get that kind of stuff. The Coca-Cola analysis, the KO, is a very different kind of analysis from growth stock queries. So if we only tested on Apple and NVIDIA, we might get false confidence about how good our agent is at doing financial analysis, because those are huge tech companies, lots of information available online, whereas people using this to do actual stock ticker analysis are going to ask about much more obscure companies and much more complicated questions. So as you're running it, you will see your traces begin to stack up. My traces look a lot more complicated than your traces right now. Don't worry about that. We're going to add all of the complications as we go. Yours are going to be really short little rows right now. You can see all 13 of them now because I ran 12 plus that original one. The initial Tesla query is there. And before we write any evals, we have to look at the data. This is what I said at the beginning we were going to do. A lot of people just hand wave away looking at the data and like, you look at your data, what does that actually mean? You should, when writing a real eval suite, be actually reading traces on a regular basis. This is not something that we're doing just in a lab. It's not something you do just in theory. You have to read the traces when you are putting together your initial evals, because that is how you know what the agent is actually producing and what you should actually be testing, because it's so non-deterministic. What was the input? What was the output? What specifically is broken? Anthropic, for instance, invested a whole bunch of time and money in tooling that makes it very, very easy for them to read their agent evals. That is, and their agent outputs. That is what we are doing here for you. We are providing you with that tooling. So you need requirements first. Before you can categorize failures, you need to know what success looks like. A way that evals tend to fail is asking questions that are too broad or require context that your agent doesn't have. So you can't say it doesn't work. You can't have if you haven't defined what works means. So for our financial analyst, what does a good report look like? You can't just say the report should be thorough. You can't just say the report should be in-depth. What does that mean? So in this case, we want our agent to report actionable recommendations. We want it to be able to tell us whether we should buy the stock or not. That's a very specific thing that we need to be able to do. So it should be able to distinguish between forward-looking analysis and historical summary, because those are our success criteria. And like I said earlier, this isn't rocket science. This seems like obvious stuff, but you need to define that stuff up front and write requirements down, because otherwise you will have vague evals that are basically flipping a coin. You're like, did it do well or not? The agent doesn't know because the agent doesn't have enough context. It doesn't have enough rules to decide whether or not things are good or bad. And this is not a purely technical exercise. This is where you should get your stakeholders involved. This is where you should get domain experts involved. This is where you should get your product managers involved. This is where you should get your actual users involved, because they are the ones who know what good looks like. The engineer who is writing your agent is not necessarily going to be the best judge of what a good outcome looks like. They might say, oh, well, that looks legit to me, whereas an actual user would go, oh, this is completely useless. So it's very cross-functional. And if you can't define what great means, you're not going to be able to write an eval that checks for what a great is. So a quick note on where to get test data. We have, in this workshop, production traces because we've already run the agent. What if you're building something brand new? What if you are in development and you don't have real users to generate real trace data for you? The answer is synthetic data. Get yet another LLM involved, get it to generate a bunch of fake queries that are deliberately as across the spectrum of use cases as the LLM can imagine, to generate real traces that test what your agent would do if you gave it that data. The examples that I like are, if you give a financial analysis agent to a bunch of real users, one of them is going to ask, research Tesla financial performance. One is going to ask, what's going on with Tesla stock, which is the same question phrased completely differently. One is going to be like, yo, is Tesla a buy right now? Which is the same question, phrased for Gen Z. But they're all the same intent, but they look very different. So the outcomes might or might not be different, and you won't know until you run your evals. We're also going to need to include edge cases, so non-existent tickers, multi-part questions, jailbreak attempts, adversarial stuff. They might just be 1% of your traffic, but they're the 1% of your traffic that tends to end up on Twitter when your agent goes completely off the rails. So your test data should look like production data. The best place to get eval data, test data, is from production. Throw the agent into production and get some stuff. If that is too dangerous, then synthetic data is your next best bet. Now let's examine those traces. If you've been running it in the background, you should probably have finished generating those traces by now. So let's see what Apple did. I wanted to be able to, go to specific things that went wrong in specific ways, which is why all of my data is pre-generated, because it's all non-deterministic, so I couldn't predict that it was going to go wrong. So Apple's one did a really funny thing, which is it did a whole bunch of research, and then it tried to write the output to a file, because it thought it was Claude code, and it was like, oh, you wanted a report, so I'm going to produce a markdown file on disk for you. And then it tried to call the write tool and then completely failed because it was running in a notebook which doesn't have write permissions. And this was a real failure of the agent that I didn't predict when I was putting together this demo. I was not expecting that it would try and write to disk. I didn't ask it to do that. I was just too vague about my requirements of write a report. Write a report to the output, not to the disk. So what actually happened with Apple? What did it say? It presented a concise financial report, but it didn't say whether I should buy it or not. It just said, dominates in near-term profitability and market cap, which is nice, but not what I wanted, right? I wanted something to tell me whether or not I should buy this stock. The NVIDIA report was likewise very thorough but not actionable. It didn't tell me whether or not it should buy it. Which other ones were interesting? Let's look at the NVIDIA one because it is cool. Where did I put NVIDIA? There it is. So it did 4 web searches, including the competitive landscape, specific competitors, stuff like that. And it actually did the output correctly. It wrote the output to the agent itself. But this is why you have to read your traces, because if I'd read my traces, if I hadn't read my traces and I just judged it on the output of the Apple one where it tried to write to disk is complete garbage. But it's not because it didn't write the report correctly. It had all of the data that it needed. It did all of the web searches correctly. It wrote a good report. It just wrote it to disk and then failed. So you need something that you need to be reading your traces because you need to know these unexpected outcomes are happening. And if you click through all of these traces, you will see that, how quickly can we, yeah, you can see that the write failure happens multiple times. So there is a pattern there. Just by eyeballing it, we can see that it tries to write to disk multiple times. This is a systemic failure in our agent that we're going to have to address. So the last one is an example of confidently wrong. This is the last one I'm going to click into. The Rivian report. It includes all sorts of stuff about Rivian. Like it, shipped 62,000 to 67,000 vehicle deliveries in 2026. Did it make that up or not? I have no way of knowing because I don't have the information about Rivian, and Rivian's information isn't particularly public, so that is a suspiciously accurate number for a company that doesn't share its financial results. So again, reading the traces, I'm going to look at that and go, right, that's a situation where I should be checking carefully whether or not it is hallucinating that information, whether or not it really got that research data from somewhere that I trust. And when you find a failure, you have to ask why it failed. So the response was wrong as a symptom. Did it get bad research results? Did it try to write to disk when it shouldn't have? Did it have the right data but produce the wrong conclusion? Did it make up a stock price? Each root cause points to a different fix. So the thing that you have to do with this data is categorize it. Looking at individual traces is very, very important. And then you produce en masse a pattern of where things are going wrong, not just going wrong once in a while, but going wrong systematically. And like I said, you can use an LLM to do that. You can use an LLM to run through all of your traces. There are APIs to do that in Phoenix. Examine all of your output, annotate your traces, and say, this was bad for this reason, this was bad for that reason. And in a real data set, you're going to soon find patterns emerging. In the notebook, I have printed a rough and ready graph of things that went wrong. I went through my trace categories. I said, things that were good and bad. I printed them out, and then I got it to produce a table. So root cause frequency, it mostly looked good. Possible hallucination, reasoning gaps, unverifiable data, missing recommendations. It's easy to look at this graph and say, okay, so possible hallucination is the most important thing because it's the one that appears most often. But in reality, you need to be more subtle than that. If it went completely off the rails and started, spewing the text of Moby Dick to the user, that is a complete failure, a very severe failure, and that is more important than a possible hallucination. So you need to sort of multiply your severity times your frequency to figure out your priority when you're deciding which system to look at most commonly. And fix the expensive, frequent failures first. So the expensive stuff is where it's gone completely off the rails, and minor hallucinations you can probably get away with. I wanted to introduce the Swiss cheese model, this diagram blatantly stolen from Anthropic's blog post. It's a concept borrowed from safety engineering. You have to imagine each layer of defense as a slice of Swiss cheese. There is no set of evals that are going to be perfect. They're all going to have various flaws and various holes, but if you layer them, the holes aren't going to line up. So eventually you will stop all of the possible ways that your agent can fail. Stacking your eval layers works like that as well. So your code eval catches a bunch of really basic stuff first. Your LLM-as-a-judge catches reasoning gaps but misses subtle hallucinations. Your human review captures things that got through the first two layers, but it can't scale to every trace. So no single eval method is going to capture all of these ways that it can fail, but if you use them all at the same time, you're going to do a pretty good job of evaluating your agent. So let's talk about the actual evals. Let's write some real evals, and starting with the simplest type of eval, which is a code eval. Our agent is supposed to analyze stock tickers. So the most obvious thing to do is to test whether it mentioned the stock ticker in the output at all. Was it talking about the company that I was expecting it to talk about? That is a completely deterministic test. I don't need an LLM to do it. I can just search for that string. So that is what I have done in the notebook. And I'm just going to walk very quickly how that works. So first, we have got our spans from the AIE Cloud Financial Agent. This chunk here is us getting the parent spans. Every single log line is a span. The ones that are the root in that graph that I showed you, they are the ones that have no parent, so that is how you detect your root spans. The important ones are the ones that have no parent, so that is what it's checking for there, ones that have no isParent set. And we found 13 top-level spans, which is correct. This is what a code eval looks like. We use the create evaluator decorator. We give it a name. This is what it's going to be sent to Phoenix as. This is the name of the eval. And we give it a kind, which is code, which is to tell Phoenix that this is a simple deterministic eval and it doesn't need to run it as an LLM. And then it's just a regular Python function. You can also write them in TypeScript if you prefer. This is a very basic regex. I went looking for phrases in capital letters, and then I excluded some phrases that are not stock tickers, and then just went basically looking for the stock ticker in the text of the output. And that is a very simple and very easy and extremely effective first line of defense. Did it write anything at all that mentioned the company that I was asking about? So we can get the results here. We can run the this is how you actually run that eval. You evaluate data. You run evaluate data frame. You give it the evaluator, which is the mention sticker function that we just passed, and you give it the data frame of parent spans, which are the ones that we just did. One thing you should notice here is that we are doing with suppressed tracing. We are using Anthropic to do the evals. So by default, Phoenix is going to pick up that Anthropic is being run. And so it would, if you don't suppress tracing there, you will get the traces from Anthropic running the evals itself, which is very confusing. So you just tell it, when you're actually running the eval, don't capture the traces. That's why that's there. We can see that it passed 11 times out of 13. So the Tesla report and the Amazon report, neither of them actually mentioned the stock ticker of the company that we were expecting. So even this very, very basic deterministic code eval has found a problem with my agent. So why did it do that? We have to look at those. We have to look at the spans to find out. If you look at the spans to find out, you'll find that Tesla is one of the ones where it failed because it was writing stuff to disk. Amazon was more interesting. It wrote the entire report about AWS and didn't mention Amazon at all. It just assumed that I meant AWS, the one part of Amazon, and not all of Amazon. That is a learning that we wouldn't have got if we were just testing input and output, right? That's what the explanations are for. But what this proves is that code evals aren't just toy examples. So JSON parsing, length limits, forbidden phrases like, as an AI language model, I cannot. You can test for those deterministically. And a code eval doesn't have to be a simple string operation. It can query a database to verify that your product pricing was correct. It can call an API to check a stock price. Anything with a grading always gives the same answer. You can use a deterministic code-based output, code-based eval to get the answer and test things. So one of the things that you should be careful of when you're writing a code eval is that you should be testing what the agent produced and not the path it took. I mentioned this earlier. So don't get it to look for all of the steps that you think that it should have taken to be able to get to that answer. Just check whether it got the answer you were expecting. You can also be flexible in your parsing of strings. So if one of the things that you were asking for was like a time estimate, the agent might say, 2 hours, or it might say 120 minutes, or it might say a very large number of seconds, all of which answer to 2 hours, you can put your code eval to check for all 3 of those things as a valid output. And the path the agent took matters less than where it ended up. You want the answer was right, but you got there the wrong way, not to be something that your eval is looking for. So let's move on to step 5, which is the built-in eval. In this case, we are going to try using one of Phoenix's built-in evals, which is the correctness evaluator. This is using LLM as an eval to do things that no deterministic check could do. In this case, we wanted to tell us whether or not the output of the agent was correct. Was it factual? So, the correctness evaluator seems like the one that we should go to. Every LLM-as-a-judge eval has 3 parts. It has a judge model, which is the LLM model that does the grading. It has a prompt template, also called a rubric. And it has the criteria, which is the criteria the judge applies, and it has the data, which is the examples being evaluated. Phoenix keeps those 3 things separate so you can mix and match them, which is very useful. You can try the same evals with different models. You can try the same model with different evals and compare how your evals are working. So like I said, correctness checks whether a response is factually accurate, complete, and logically consistent. It is an eval that we wrote, a prompt that we wrote that is built in. You can inspect the prompt that we've written so that you know that it's not just a black box. And we also have things like evals for tool selection. So did the agent pick the right tool? Tool invocation, did it pass the right arguments? We have built-in evals for document relevance, refusal detection, lots of things that you would want to check in a real eval that you don't have to write yourself because every eval suite needs to run these tests, so we built them in. What we want to know is, was it correct? So let's set up the judge. We're going to, like I said, we're going to use the built-in correctness evaluator. First, we need an LLM to give to it. We are going to pass that LLM to the correctness evaluator, which we've just pulled in. If you wanted to, you could print out the full prompt here. We're going to suppress tracing again, and then we're going to say evaluate data frame just like we did before. We're going to give it the same set of parent spans, and we're going to give it a different evaluator, in this case, the correctness eval. And we're going to display the first 5 results from that. This is a blizzard of information. Once you've got the information, you have to send the results to Phoenix, and that is what is happening here. So you turn the results of the eval into a data frame, and then you pass that data frame back to Phoenix using the log span annotations data frame. The judge that we're using to do this is Sonnet. Like I said earlier, you want to use a more capable LLM to do the judging than you used to do the actual agent in the first place, because that LLM is going to be smarter and it's going to catch things that the original LLM did not. If you are already running an agent in production with Opus, there is nothing better than Opus that you can use to be your evaluator. But if you are running an agent in production with Opus, you probably don't care. The other thing that we have to do is we rename our input and output so that the agent understands. I'll show you that in a second. So yes, my speaker notes and what I'm actually doing on the thing, I'm going so much faster in the notebook than I am on my speaker notes, so I apologize. So let's actually run that result. And look at it in Phoenix. You can see that I have a correctness annotation next to every single eval now. And there's a problem, which is if I look at the correctness overall, I'll see that every single one of them was 0. All of your evals are incorrect. Why are your evals incorrect? We have to figure out why that is the case. We need to click in, and we need to look at the explanations. So let's look at our annotations. Let's look for correctness, and let's actually just read the annotation, which is that the output presents highly specific financial figures for Q1 financial year 2026, but the problem that it keeps having is that it thinks it's 2025 because it is a model trained in 2025 and it doesn't know what date it is and it doesn't have up-to-date information. Our correctness eval is, in this case, complete garbage because it is trying to base it on its knowledge of Q3 2025 or whenever it was that Anthropic trained Sonnet. And it doesn't know anything about the 2026 look-ahead stuff. So our correctness eval in this case is completely useless. That is itself a learning, right? If you were asking it more general knowledge questions that could be judged from an entire trawl of the internet, it would have done much better. But in this case, we're asking it for very, very up-to-date, very future-looking stuff. And our built-in model, our built-in eval can't do it. So it tells us that we need a different eval. What we need is a faithfulness eval. The faithfulness eval is basically, if you're familiar with RAG applications, it's going to check whether or not the output of the agent was based on the information that we gave it. So conveniently, suspiciously conveniently, I split up our agent earlier into 2 steps, one of which does the research and one of which does the output. That means we can take the step where it did the research, take that output, and give it to our faithfulness evaluator and say, based on this research, did it correctly judge? Did it correctly write a report? Did it write a report that is based on this research and only this research? Did it stick to the source material? So let's see what that looks like. We get the same set of child spans, exactly the same set, and we have to do the input massaging that I mentioned. We have to take the inputs and turn them into the inputs that the faithfulness evaluator is expecting. And we have to produce a context column, which is the output of the first turn of the agent and only the first turn of the agent. So that's what that code there is doing. So that gives us input, output, and context, which are the 3 columns that our faithfulness eval is expecting to run on. So let's actually run it and see what happens. We added the context. We can run the context. We suppress tracing again. We take our parent spans. We run them through the faithfulness eval, and we give it a data frame this time, which is the spans with that context column added. And we get our evaluation of 13 out of 13. And we get that all 13 of the 13 were faithful. So correctness gave us 0 out of 13 passes, but faithfulness gave us 100%. So we've managed to, one-shot our faithfulness. 2 built-in evals, 2 very different signals. That's a really important lesson. Choosing the right eval can matter more than tuning your eval. Some of your evals are going to be completely useless. Some of the built-in evals are going to be exactly what you need. And that is the lesson there. Here's what you see in Phoenix for that stuff. You can see our faithfulness eval got 100% correct. You can sort by score if you want to find your best performing or your worst performing. In this case, that's not going to do anything because we just have a 1 versus 0 score. But you can filter. So you can filter to show only failures. So in this case, I'm going to look for my actionability ones. No, actually, I'm going to use my correctness ones. Correctness. Incorrect. I'm sure you're all being delighted by me watching it. So this allows us to filter down to only the ones where we got a correctness of 0. And you can click into any of those failing traces to see the full execution, exactly what went wrong. So when there's only 13 of them, that's not super useful. If you had 1,000 of them, that would be really useful because you'd be able to find only the ones that are failing and focus on them. But built-in evals are only your starting point. They give you an immediate sample, an immediate signal without any prompt engineering. When you get into the real meat of evaluation is when you do custom code evals. Sorry, custom LLM-as-a-judge evals. I mentioned earlier that one of the things that we want our agent to do is to provide actionable results. We want it to tell us whether or not we should buy this thing. There's no built-in eval in Phoenix, which is this an actionable financial report? We are going to have to write that ourselves. Which brings us to step 6, which is writing a custom eval rubric. It is worth talking about how to put together a good eval rubric before we actually do it. Every good eval prompt I've seen has five different parts, 5 important parts. And I'm going to go through each of them. First one is defining the judge's role. You have to give the judge domain context, tell it what kind of output it's evaluating, and what that output is supposed to accomplish. This is an example of doing that. The "you are an expert financial analyst evaluator" is something that everybody does. Tests show it doesn't make that much difference, but it does make some difference, so you may as well throw it in there. What really makes the difference is the instructions and the rest of the prompt. So part 2 is your criteria, and this is where you should be as explicit as you can possibly be. This is where a lot of people underinvest. So like I said, don't say a good response, because that is an aspiration. A good response doesn't have any context about what defines good and what defines bad. A good response is helpful and accurate. Sounds like you're doing better there, but helpful is also completely vague, and so is accurate. Nobody knows what that means. So instead, list exactly what makes a report actionable and list exactly what makes it not actionable. What makes these criteria specific enough to actually work? They are specific and observable, contains specific recommendations, that is something that the judge can check for, includes forward-looking analysis, not just historical data, that is a clear distinction. And on the not actionable side, only summarizes publicly available data without interpretation. That describes a particular failure mode that we've already seen when we were looking at our traces. We saw it, just giving a general "Apple is good," kind of, I guess, response, which is not what we wanted. And each criterion maps to something we actually observed in our traces earlier. That's what I'm trying to get to here. You shouldn't just be writing rules on the basis of what you think would be a good idea. You should be writing rules based on the actual traces you've seen and the actual failures that you've observed. Part 3 of a good rubric is you should present the data clearly. We use begin data and end data in our Phoenix built-in evals. If you're using Claude, Claude really loves XML, so you can use XML tags to begin and end, and it's very good at judging the start and end of things. But what you're doing with them is you are labeling each piece of data clearly so that it can tell the difference between what these pieces of data are. So user query, financial report, clear boundaries, reduce the chance that the judge is going to confuse the query with the report or vice versa. Part 4 is adding labeled examples, and this is the part that most people skip, and it is by far the most useful thing that you can add. If you take one thing away from this whole section on custom rubrics, it is that you should be adding examples, because LLMs are really good at looking at an example, figuring out what the pattern is from that example, and then following that example. And they are much better at that than they are at getting a list of instructions that just say, this is what you should do. They are really, really good at looking at the example and following it. And this is what an actionable example looks like. It has everything. So it has specific data. It has identifying a concrete risk with a number to back it up. It has specific recommendations, accumulate below a certain price. That is what actionable looks like. This is what not actionable looks like. It's not wrong. NVIDIA is indeed a major player in the semiconductor industry. It's just not telling us whether or not we should buy the stock. So that is just a description. It's not a demonstration. And the 5th thing that you should do is you should constrain the output. We want to say, is this financial report actionable or not actionable? Output 1 word is a thing that your rubric should nearly always have. Just tell me whether it's actionable or not actionable. Do not give me a long explanation. Do not give me a JSON block. Do not give me a markdown diagram. Binary is really clear, and if you genuinely need more nuance, you can give it 3 categories. You can say, like, it was incorrect, it was partially correct, or it was completely correct. A thing that a lot of people want to do, because it seems like a good idea, is a rating. They're like, give me a percentage, or give me a score from 1 to 10. These do not work very well. what is the difference between a 6 and a 7? Can you define exactly when you are judging something from 1 to 10, what is the difference between a 6 and a 7? Unless you put that into the rubric, the agent can't do that either. So it's just going to introduce noise into your ratings. So yes or no, and if you really need to, a maybe, but no more detailed than that. Another practical tip is when you're writing an eval is to get it to think out loud about what it is doing. Chain of thought for judges demonstrably improves how the judges work. So you tell it to explain its thinking first before it outputs that label, and that is measurably, demonstrably going to improve the quality of the output that you get because it's going to do a bunch of token generation before it decides whether or not the thing is good. So if you are coding along, now is the time for you to see if you can write a better eval than I can. This is what a custom LLM-as-a-judge looks like. It is just a really big prompt. This has all of the things that I just mentioned. So you are an expert financial analyst, list of things that make it actionable, things that make it not actionable, an example, a begin data and an end data block where I've put in the input and the output. And based on the criteria above, is this financial report actionable or not actionable? You are probably not going to be able to write a better, like off the top of your head, going to be able to write a better prompt than this because I had a lot of goes at it. But it's fun to try, so feel free to plug in your examples of what an actionable report should look like now, and then we're going to write it down. To actually use this, once we've written our prompt, we are going to use a helper called the classification evaluator. This creates an LLM-as-a-judge for Phoenix, and we only have to give it 4 things. We have to give it a name, actionability, which is the label it's going to show up with in Phoenix. We have to give it that prompt template, which is the thing that I just showed you above. We give it an LLM because it has to do the judging somehow. And then we give it choices, which are labels with scores. So it's either actionable, which we're saying is a 1.0, or it's not actionable, which we're saying is 0. Once again, we suppress tracing. Yep?
Okay, sorry, so what about the chain of thoughts thing? We're not saying, first write your reasoning and then just...
That's true. I left that out. I told you you should, and then I didn't. Well spotted. Somebody's actually paying attention. This is amazing. Because it's really warm in here, and it's like 4:30. So let's look at the scores and see what stuff came in as an actionable and what did not. This is a capability eval. I was talking about regression evals versus capability evals. This is a perfect capability eval because it's not doing very well. In 6, I think, of the cases, it came up with actionable stuff, and in the rest of the cases, it came up with not actionable stuff. That means it has a hill to climb. That means that we can tell the agent to get better. And it's actually going to have some headroom to get better. So we log the annotations back to Phoenix, and now we can look at Phoenix, and you can see the actionability scores inside of Phoenix. We can do the same filtering that we did before. Actionability. I did not think about when I was doing this whether or not I was going to be typing with one hand. I would have chosen shorter labels. Right. So that's actionable, or we can say not actionable, and we can get the ones where it failed. And we can, like we did with the other ones, we can click through to our annotations, look for actionability, and get an explanation. So we can say the financial report as described lacks a concrete buy, sell, hold recommendation. Haiku is messing up here. This is why we picked Haiku, because it was going to mess up. You can filter and sort by anything. So you can filter by latency, you can filter by number of tokens, you can filter by cost. You don't have to filter by just your labels. So one of the ways that you can use that is, for instance, if you have an agent that is getting the right answer but very expensively, right? It's doing 100 web searches and eventually getting your answer. That is not good in production, and you can go and look for those expensive calls, those expensive operations, and tweak your prompt such that it does things in a cheaper way. So you don't have to just, Phoenix is giving you a bunch of things to search for that are not just the stuff that you put in. It's giving you a bunch of extra information. Like I said, this one, it said that it lacked a concrete buy-sell hold. If we filter through to other ones, we can get other actionability explanations. The report presents strong financial data and forward-looking analysis and provides context, but the absence of an explicit recommendation or actionable investment directive places it in the not actionable category. Great, that is what we wanted this thing to do. So you should be treating your evals like code. Your evals, the wording of that prompt that we just put together of how exactly to measure whether or not your agent was doing a good job is going to drastically change word by word inside of that prompt because LLMs are so non-deterministic. So you should be versioning your prompts, you should be storing them, you should make sure that you know like 5 versions ago what did this prompt do if things go radically off the rails. And you should test them on examples where you know the right answers. So if the judge disagrees with your human labels on 40% of examples, that means the prompt you've written is not very good. You can iterate on rubrics without touching code. An eval that you haven't validated is just a fancy way of being wrong at scale. One other thing that I want to flag in writing custom evals is, in custom LLM-as-a-judge, is the God evaluator. It is very tempting to write a single LLM evaluation that tries to test for everything. So it's going to test for accuracy, tone, completeness, policy compliance, formatting, and don't do that because it is a nightmare to calibrate. If it fails, you don't know why it has failed. You'd have to get it to output an extra word saying, this is one of the 5 things I was testing. Instead, split your evaluator into one thing per dimension. So test for accuracy, test for completeness, test for tone, but test for all of those with a separate LLM eval. I want to talk about guardrails versus North Star metrics. Some evals are guardrails, like they're ship blockers, like if the agent hallucinates a stock price, that's probably a hard fail for this one, right? We don't want it to say buy when it should have said sell. But if we say that you should always recommend complementary investments, that is a nice to have, not a deal breaker. So you need to know which of your evals is which ones should be ship blockers, and which ones are just informative. Meta evaluation is the thing that we've been dancing around so far. How do you know that this custom rubric that you've written is actually working? How do you know that this code that you wrote that is now saying whether stuff is actionable or not actionable is trustworthy? The way to think about it is your judge is a classifier. It is an ML classifier. That is the mental model. So it takes an input and it makes a prediction. And just like any classifier, you can measure its performance by comparing its predictions against ground truth. So in this case, your own human judgment you can use to check the LLM's work. The problem with human judgment is that it involves a lot of human effort. You have to actually look at the results of your evals and compare them manually, saying, do I agree with it in this particular instance? If I go into a span in Phoenix, I can add an annotation. So in here, I could create a new annotation, which is like, does the human trust this? And say yes or no. And I can do this programmatically, or I can do this in the UI. And I can put in a whole list of human evaluations of my evaluations, whether or not I think these things are actionable. And then I can do a comparison of the LLM-as-a-judge to my human annotations. I'm not going to go into the detail of how that is done, because it is boring. But what we're doing here is we are building a golden data set. Golden data sets are incredibly helpful. I mentioned them right at the beginning. They are a way of measuring whether or not your evaluator is doing a good job. And the way that you do this is the same thing that the LLM did. You should give yourself real concrete criteria for deciding whether or not this thing is a success or not a success. So don't just go in as a human and be, yes, it worked, or no, it didn't work. because that is, you're going to have the same problem the LLM is having. You're going to be arbitrary. You should be essentially reading the same prompt that you've given the LLM and deciding whether or not you believe, according to these rules that you've given yourself, whether or not this thing is or is not actionable. So give yourself examples, eliminate ambiguity, and eliminate the chance to get lazy. As you do this, you should keep your tasks unambiguous. If your agent scores 0% consistently, that's almost always a broken task. That always means that your agent is failing to do anything. So it's not a good eval. This can happen if you've made your eval task something only a human could do, and you've made it something that your agent couldn't possibly manage. So the way to avoid that is for each task, create a reference solution. Decide in advance what it was that you wanted an LLM to have output in this situation, and then you'll be able to judge whether or not the LLM is getting anywhere close to that. You can also test in both directions. You can test cases where the behavior should occur and cases where it shouldn't, and you should only test, for instance, if you had a test that was, does it search the web? That is absolutely a thing that you'd want a financial agent to do. You could accidentally create an agent that cheats the eval. You could create an agent that always searches the web whether or not it needs to. So you need to make sure that you have test cases in your eval set that are, this is a case where it doesn't need to search the web, and did it not search the web when that happened. And your golden set is not just test data. It is the encoded judgment of the people who know your domain the best. So it's going to grow as you find more test cases. And today's production failure are going to become tomorrow's test case. If you're doing this for real, the other thing you should do is you should split your golden data set. It is possible to create an eval that is overfit to your golden data set. It passes your golden data set, but it hasn't properly generalized. It's just accumulated a bunch of examples of exactly your golden data set, and so it passes them. So you should split your golden data set 75-25 into the ones that you are training it on and the ones that you tested against. So every time you make a change to your prompt, you can then run against the 25 that it's never seen before, and you can see whether or not it actually does a good job. So let's run our actionability judge. On the exact same examples that we did before, I've used a span query to do the filtering, just like we can do in the UI. And I've got only the failing ones. Sorry, no, I've got the human actionable ones. And I've done this line here where I've taken the complicated attributes.input.value and turned it into input, and attributes.output.value and turned it into output, because that is what our eval is expecting. So now let's see whether our agents disagree or agree with the annotations that I put in about human actionable stuff. What we get here is 2 out of 6 times my human actionable label and my actionable label have disagreed. I will confess that what I didn't do is actually come up with human actionable labels. I just assigned human actionable versus not actionable kind of at random so that I would have some real data to point out, because I only have six answers here, 6 places where it failed. And so it's really not enough to do a real set. A real set would be 20, 50, 100, 200. So to have actual data to look at, I just put stuff in at random. But what this gives us is, if I had done it for real, what this would give me is a sense of whether or not my human judgment is matching up to the judgment of the LLM. This is my golden data set testing against the LLM-as-a-judge and figuring out where they disagree. Which brings us to rubric iteration. In the same way that we can take our agent and we can improve our agent by improving the prompt, we can take our LLM as a judge and we can improve the LLM as a judge through iteration. To do that, we need to think about precision and recall, which are more of those opaque ML terms that the researchers snuck into our AI engineering lives. They're not that complicated. Imagine a spam predictor. A spam predictor is going to say whether stuff is spam or isn't, and you can compare your spam predictor against whether or not things are actually spam. So there's 4 possible outcomes. It can say that it's spam, and it is spam, which is a true positive. You can say that it's spam when it's not spam, which is a false positive. You can say it's not spam and it's not spam, a true negative, or you can say it's not spam and it is spam, which means that you missed. Machine learning engineers have 2 ways of measuring this data, and they conflict with each other. So you have to pick, you have to decide for your use case which of these things you want to optimize for. So the first way is precision. Precision is out of the number of true positives out of the total number of positives. If you've got high precision, that means you've made the false positives number small. That means you're minimizing false positives. If you're in a use case where false positives are really dangerous, that is what you want to do. That's great for spam, for instance, because you don't want to send a real email to spam, and you are OK with getting a certain amount of actual spam in exchange for not doing that. But recall is the opposite. It is out of the real positives and the misses, what percentage were really positive. This is, for this one, to make it go up, you want to minimize the number of misses. You want to minimize the number of false negatives. A good example of when you do this is if you were doing like health stuff. If you were doing cancer screening, you would absolutely want as few misses as possible. You are OK with a ton of false positives when you're doing cancer screening, as long as you don't miss somebody who actually has cancer. So these 2 measures are going to go in opposite directions if you optimize. So you have to pick one for your use case and decide how to optimize it. So let's look at what that looks like in practice. I wrote a bunch of code here that calculates all of these things, and it came up with precision and recall for my judge. So the precision of this one is really good. When the judge says fail, is it right? 100% of the time, it is correct. And its recall is really bad, which is of all the real fails, how many does it catch? This is what you would expect. You would not expect to get 100% on one of them. So I have made something that is really good at precision. It's really good at avoiding false positives. With such a small sample, these numbers are basically useless, right? You want a golden data set of 50, 100, 200 things, and then you're going to get real numbers for precision and recall. This is very much a toy example. And in most eval scenarios, you're probably going to want to prioritize recall, because it is better to flag a few false positives than to miss real failures. A false positive just means you have to review something as a human. That's actually fine, whereas a missed failure means that bad output reaches your users. But like I said, there are some use cases, for instance, medical use cases, where you'd want to do the opposite. A few known pitfalls with using LLM judges are worth keeping in mind. One is position bias. If you present 2 options, the judge tends to favor, depending which model it is, either always the first one or always the last one. There's length bias. LLMs prefer longer responses over shorter responses, just in general, and will tend to prefer them. There's confidence bias. Your judge can get fooled by a response that sounds confident, just like humans can. And there's self-preference bias. If you're using the same model to judge as you are to generate the output in the first place, they tend to like their own output, which is another one of the reasons that we use a different model as a judge than we do as the one that is running the agent itself. You can also consider using a completely different provider. So you can use Claude to do your agent. You can use OpenAI to do your evals. And you're going to get more reliable evals than you would if you use Claude for everything. How do you know if these biases are affecting your results? you have to track judge accuracy across different categories of inputs. So if the judge always passes long responses and always fails short ones, then you know that you've got a long bias problem. If it passes everything from one category of query and fails everything from another, you have to dig into why. Your benchmark here should be human performance, not perfection, which is the last thing I want to say about meta-evaluation. If you give two humans the task of producing your golden data set and say, tell me whether or not, for instance, this report is actionable or not actionable, they're not going to agree all the time. In fact, they're going to disagree a surprising amount of the time. Inter-rater reliability is often as low as 0.2 or 0.3 of the time. So two experts, the same output, the same rubric, and they will disagree. So if your LLM judge achieves higher consistency with you than that, if it achieves 0.4, it's doing really, really well. So the judge disagreeing with you is not necessarily a reason to throw out your eval. It's if the judge disagrees with you more often than a human would disagree with you. The other thing you should do is that your failures should seem fair. This is something that Anthropic brought up when they talked about meta-evaluations. When a task fails, it should be clear what the agent got wrong and why. So if you look at a failing trace and think that answer looks fine to me, the problem is probably the eval, not the agent. This actually happened at Anthropic. Claude Opus initially scored 42% on a benchmark called CoreBench, and that seemed low, and they went and looked into what it is that CoreBench is actually doing, and they found multiple problems, not with the model, but with the eval itself. For instance, the eval was checking for an answer of 96.12, and Claude was giving it the answer of 96.124991, and it was saying, no, that's not right, because that's not what I was expecting. After fixing the eval, Opus's score jumped to 95%. So your evals can be can be judging things as wrong when they are just being too strict, or they are judging something that is not what you were trying to judge. And the lesson here is that you should not take evals at face value. You should always be looking into the explanations of your evals. You should be looking into the output of your evals. You should be checking it against the golden data set to make sure that you're actually improving the agent. So the step 7, and the last thing, I'm sure you'll all be glad to know, is data sets and experiments. This is how you go from just measuring whether things are wrong to actually improving your agent. So you've found some failures, you've read the explanations, you know what to improve. So you change the prompt, and then what? How do you know that your fix actually worked? How do you know that you have improved your agent? How do you know that you didn't break something that was working before? If you just run the agent again on a couple of examples and eyeball it, that's just going back to vibes. You need a systematic way of testing whether or not your changes to your evals, to your agent, have actually improved your evals in a systematic way, and that is what experiments are for. So for this, we go to a completely different part of the Phoenix UI. We go to the, whoops, there we go. You didn't see that. We go to our experiments evaluation. To do that, you can go to produce your data set, you go to your traces, and you take, for instance, a bunch of failing traces, and you click Add to Data Set. You can create a new data set using this little plus here, or you can add to an existing data set, and that gives you, in this case, AI agent financial failures. So you can click through to examples, and you can see I've taken the 6 times when our actionability trace failed, when our actionability eval failed, and I've put them into a data set, because this is what I want to do. I don't want to run all 13 every time, or in production, all 1,000 every time. I want to run my new prompt against only the times that it failed, and I want to see if it's getting any better. So now we improve the agent. We can look at what the evals told us. The actionability eval said that some reports were not actionable because they summarized data. They didn't give explicit recommendations. So we can update both prompts. The research prompt, like I said, now explicitly requires specific financial ratios. It requires recent news, current price data. And the writing prompt now explicitly demands a buy, sell, hold recommendation. That's happening here. If you are still coding along, well, all the power to you. And this is where you can try and do a better job than I did of improving the agent. You can give it a better research prompt. You can give it a better write prompt. Notice how every change that I've made to the prompts here maps to a specific thing that we found wrong in the evals. I'm not just randomly changing my agent prompt. I am changing it in response to specific things that we noted in the evals. So financial ratios, news from the last 6 months, a buy, sell, hold recommendation. Those were things that in the explanations from our previous LLM-as-a-judge, it said were missing. And we've said, OK, include those things. So we are not just getting a notice that we are wrong. We are getting direction from our evals on what we could do to do better. And we are feeding that directly into our agent and making the agent better that way. This is data-driven prompt engineering. This is what Arize is all about. It's about taking a bunch of stuff that LLMs tell us about what is failing and what is not failing, and turning it into real improvements to our agent. So now let's run an actual experiment. To do that, you need a task for your experiment to run. In this case, it is our improved financial report. It's basically exactly the same agent again. And we've taken that agent and we've put it into a task function which just runs that agent with the input and output that we're expecting. We've created a new classification evaluator, again with the label actionability. We've given it the same actionability template, and created this new evaluator, and now we are running we are fetching our data set of just the failures, and we are going to run our async client, which is faster, basically, against that set of just the failures. So you can see here, ta-da, my improvements to my agent have one-shotted the agent from getting 5 out of the 13 responses as actionable or not actionable. And it is all 6 of my previously failing tests are now running correctly. So you can see that here. You can see the results in this graph. What I've done here is not how it would look in production. If you were in production, you would have made some very small change to your prompt, and you would have got some very marginal improvement across 1,000 sets, and you would get this graph of your agent slowly getting better at all of these things. I've one-shotted it here because it's already been 90 minutes. We need to get out of this thing sometime. But this is the hill that you're climbing. This is literally how you get from 0 to 100% score, is you measure inside of your experiments, did my prompt change prove anything? Did my experiment get a higher score or a lower score than next time? Sometimes you're going to make a change that's going to make your score get worse, and you're going to have to undo it, go back to your previous version of your prompt, change something else. That's why you treat them like code. The key thing here is that a Phoenix experiment doesn't care what your task does at all. So in this case, the task that I gave my experiment was run the full agent again against a new set of data. But if our eval had told us that our tool calling was bad, I could have just run an eval that only runs the tool calling, and that would have been much cheaper and much faster than an eval that runs the entire agent. So you can run experiments against a chunk of what your agent is doing, a small subset of what it's doing, and improve that part without having to expensively run your whole agent every single time. The power of experiments is controlled comparison. You get the same inputs, the same evaluators. The only thing that's changed is the agent's prompts, and that means that any difference in scores is attributable to your change. You're not wondering whether it scored higher because of your prompt change or because the web search happens to return better results this time. You've eliminated a major source of variation. Ideally, what you do is you run each of these multiple times to account for the non-determinism of your output. That is the pass at k concept that I'm going to touch on just towards the end. But for now, a single run per example gives us a good enough signal to tell us whether things were right or wrong. And this eval iterate cycle is where the real value lives in evaluation. You get your results, you improve your results, and you slowly improve your app. One of the things that you could do at this point is say, why am I as a human doing this at all? What if I got the output of the eval and gave it to Claude Code and said, hey, Claude Code, go back to my app and improve it somehow? And that is closed loop evaluation, which we think is very exciting and is definitely going to happen as the models get better, where you've written the initial version of an app, and then you use evals as the feedback mechanism to your coding agent, which then automatically improves your app without you needing to be involved at all. I'm not doing that here because, again, we've all been sitting here and we're very warm, so I'm not going to stretch my welcome any further than I've already stretched it. A good question that you probably have is how many samples do you need? I've mentioned 50, 100, 200, 400 samples. You don't have to just eyeball this. You can use math. If you are aiming for an agent that fails only 5% of the time, or 3% of the time, 200 samples, a 3% defect rate, will give you 95% confidence interval, which would be anywhere between 0.6 and 5.4%. 3% of failure sounds good, right? 3% is less than 5%, which is what you were trying to get to. But because of the confidence interval, your actual failure rate could be anywhere from 0.6 to 5.4%. If you double the size of your sample to 400, you reduce your confidence interval to 1.3% to 4.7%, which means that you're now constantly below the 5% threshold and you can ship. But to do it, you had to double the number of samples. So that means you had to double all of the effort. You had to double the size of your golden data set. You had to double everything. So at some point, you need to make a cost-benefit analysis of like, how accurate do I need this agent to be? How much effort am I willing to put in to get this thing to be 2% more accurate than it used to be? From workshop scale experiments like today, 12 to 20 examples gets you directional signal. For shipping decisions, 200 to 400 examples is a good target. How do you make the cycle systematic? When you're iterating, where do you invest your effort? Not every change has the same impact. There is a hierarchy. This is the impact hierarchy that I mentioned right at the beginning. The impact hierarchy tells you where to focus first. Data quality fixes have by far the highest impact. If your agent is searching the wrong sources, if your knowledge base has stale data, no amount of prompt engineering is going to get you there. So you should fix the data first. Once you're sure that the data you're giving to your agent is high quality, prompting improvements are the next highest thing to do. Few-shot examples in your prompt, explicit instructions, constraints on what the agent should and shouldn't do, those are often the highest ROI changes. And then model selection comes third in the impact hierarchy. Sometimes a more capable model solves problems that prompting can't, but it also costs more, so you have to make a trade-off about whether or not that's worth it. And then hyperparameter tuning, things like temperature, top P, that kind of thing, they are right down at the bottom. They very seldom make a meaningful difference to the outcomes of your evals. One thing that you can consider doing is writing your evals before you build a feature. If you want your agent to always verify customer identity before processing a refund, for instance, you can write an eval that checks for that first, and that gives you a capability eval and a hill to climb. This is the same as test-driven development, which is to say that everyone says it's a good idea and few people actually do it. Eval-driven development in practice is how things like Claude Code evolved. Anthropic built capability evals and then gave Claude Code a hill to climb. When a new model dropped, they would run the suite and immediately see which of their bets had paid off. They'd immediately see which of the changes they'd put in advance had actually helped it do things better and which ones had not. So who can write these evals? Like I said earlier, you should be getting your non-technical stakeholders involved because they are going to have a much better idea of what good and bad are for the purposes of writing your evals. So product managers, customer success reps, salespeople, they can all contribute to eval tasks and make your evals better Sorry?
Even code evaluation?
Absolutely, because they can tell you, they can tell you a simple test would be this should be present in every single answer, and you can turn that into a code eval. But mostly they're going to be working in prompts. The other pattern worth knowing about is the data flywheel. So the more expert judgment you add, the bigger your golden data set, the better your eval suite is going to get. And each iteration compounds. So as your eval suite gets more comprehensive, your agents get better, your understanding of failure modes deepens. And what this does is this creates a differentiated data set that becomes a competitive advantage. Nobody has your evals but you. Nobody but you has this long list of production data and production evals that say, these are all the ways the agent can fail. This creates a moat that other people don't have that can help you differentiate your agent against another agent in the marketplace that is trying to do the same thing. And one last practical benefit of evals is the model adoption advantage. Like I said, new models drop all the time. If you've got a comprehensive set of regression evals, then you're going to be able to know within a couple of minutes whether or not this new model makes your agent worse or better, and whether or not you can ship using the new model. So now you'll all be relieved to know that we are nearly at the end of this workshop. Thank you all for staying through to the end. I'm very impressed with you all. I'm going to give you now a quick tour of the things that we didn't cover so that you know what to Google to go even further than where we went today. One is production monitoring. This is something that our enterprise product puts a lot of emphasis on that Phoenix does not. Once you've shipped an agent to production, you can send a certain percentage of your traffic to an evaluation suite and be consistently evaluating all of the time whether or not your agent is performing well. This can show up drops in model quality, because sometimes those happen without a model change. It can show adversarial attacks where people have discovered a way to make your agent fail, and testing against production can guard against that. And it can also test agent drift, model drift. As your use case changes, as your product changes, things that used to work in your agent will stop working, and continuous production evals can find those. You can also do cost-aware evaluation. Like I said, we used Haiku for our agent and Sonnet for our judge because those are cheap models and they go fast. But in production, you can go further. You can use different models for different types of queries. So, if the query is, what are your hours? That doesn't need the same horsepower as, analyze the comparative PE ratios of these 5 semiconductor companies. So you can do tiered model selection. You can do cheap models for simple queries and expensive models in your agent for complex queries. One of the ways you can do this is cost normalized accuracy, which is a Google phrase that I'm dropping in here just so you can Google it. It's a way of making these trade-offs concrete. It is accuracy divided by cost. So an agent that's 92% accurate at 2 cents a query might be better than one. It might be better value than one that's 95% accurate at 15 cents a query. And the evals will tell you whether or not that trade-off is worth it. And then there's pairwise evaluation. Like I said earlier, one of the things that it's tempting to do with evals is ask the agent to rate something from 1 to 10. It's very bad at doing that. A thing that it's much better at doing is give it 2 examples and ask it to compare which one is better. That is pairwise evaluation. You can say, out of these 2 outputs, which one did better? And it does a much better job of comparing the 2 because it has 2 concrete examples to work with. This is especially useful for A/B testing prompt versions or model upgrades. And then there's reliability scoring. I mentioned pass at K. Pass at K asks whether can the agent succeed at least once in K tries. And then there's pass to the power of K, which is can it succeed every time in K tries. As the value of K increases, these 2 measures of reliability diverge dramatically. Pass at K approaches 0. Sorry, pass at K approaches 100%, and pass to the power of K approaches 0. Which one you care about is going to depend on your use case. A coding assistant that eventually gets it right, that's great for pass at K. You can just keep trying and trying until it produces something that works. whereas a customer support assistant that gets it wrong after every fifth try is a failure as far as your customers are concerned. So pass to the power of k is how you would measure a customer service bot. And then there's the frontier. There's multi-judge systems where you can, your LLM as a judge can use multiple judges simultaneously to get different opinions, to look up facts. They can verify claims. But that is fundamentally the end of what we've covered today. This is the loop. You instrument, you trace, you eval, you human annotate, you analyze those annotations, you improve your agent, and then you go back again. Some final tips is, one is you should start small. You don't have to do all of this at once. Start by reading your traces. 15 minutes of reading real outputs is going to do a lot better than hours of fiddling with your prompt if you haven't read the traces and haven't read the explanations. Write one code eval as your very first eval. Check that it's in the format that you expected. Check that the string you're expecting to be there is there. And then slowly build up your eval suite from there. Create capability evals first, and then as you pass them, turn them into regression evals. Evals are infrastructure. Some teams create evals at the very start of development. Some add them once they're at scale. But the time that you need evals is when vibe checking becomes a bottleneck to improvement. When you find that changing one thing has broken 3 other things without you noticing, that is when you need evals. The first time a regression shows up before it reaches your users instead of after, you will have justified the cost of building your evals. So now is the time to go and try it for real. You already have a Phoenix Cloud account. This is the link to the Phoenix docs. And Phoenix itself is open source, so if you feel like contributing to Phoenix, that's great. And just as a final plug, I should mention that there's Arize-AX. So you can do everything that you can do in Phoenix in Arize-AX, but there are some things that you can do in Arize-AX that you cannot do in Phoenix, and they're all enterprisey things. So if your company is very, very touchy about its data, then you're going to want things like SOC 2 and other compliance measures. AX can provide those for you. If you need things like multiple teams interacting, you can do SAML and SSO. If you have a production agent that is running at billions of rows and billions of traces, we have a technology called ArizeDB that helps us do that. AX gives you session-aware agent tracing, so not just individual agent turns, but a user's entire session from the time they logged in to the time they logged out. We have an AI assistant called Alex. We have beautiful graphical representations of what your agent is doing. We have metrics, we have dashboards, we have monitoring. It is a significant upgrade in terms of the things that you can do. But that is basically it. Thank you all for staying all the way to the end. If you have more questions, I have some time now for questions. If you think of them later, I am seldo.com on Blue Sky. And you can get these slides from that URL. Thank you so much for your time and attention. Do I have any questions now, or is everybody eager to get home? OK.
Hello. So for code evals and LLM evals, can those be defined on the platform itself, so it is run by the platform rather than by individual scripts? I might have missed that in the beginning.
No, that's a great question. Code evals and LLM-as-a-judge evals in Phoenix are run on the client and relayed back to the server. In AX, they can run online on the platform itself.
Is there any chance of using something like the Anthropic batch APIs, where it uses much cheaper version of like Observability and stuff like that to parse large volumes of data?
Ask me again afterwards. There's a gentleman behind you with a question.
Hello. Oh, hello.
Yes.
For context, I work with a construction AI company, and we look at like architectural checks and compliance. And one of the issues we have is we have tons of these checks we get from architects, and we try to like scope them out to understand what it's actually we need to build.
Right.
And we don't have a ton of label data on that. But what we've been starting to do is like try to automatically have Cloud Code scope it out and then look at consistency. So if we have it scoped out 10 times, is it the same solution every single time? And we've been using like consistency as almost like an eval for complexity of the problem. We've been kind of like piecing more of these kinds of things together, calling them like meta evals, just to like, when you have a problem we're still trying to solve. Can you think of anything else like that? Like the actual problem itself, you're creating like the process of solving the problem you're creating evals for, not just the solution to the problem.
Yes, absolutely. I mean, we touched on it already with meta evaluations, right? Like a situation where you're using an LLM to judge another LLM's output immediately becomes an LLM meta evaluation. You can absolutely use an LLM to judge which of these, 10 possible agent configurations would have been the better one. That is what I was talking about with multi-agent configurations and multi-LLM configurations. You can do a closed loop situation where an agent is coming up with 5 possible prompt variations and testing all of them at the same time against the eval to see which of these variations, without a human getting involved, which of these variations is going to improve. Does that answer your question?
Yeah, it does.
Okay. In the front.
Thank you for the talk. It was really great. I had a question on how much evaluation you need to write for a feature, because especially when you run against live traces, sometimes the evaluation can cost more than the actual feature. And
Yeah.
So how do you know when you wrote enough of evaluation?
That is a really good question. How do you know when you have written an evaluation that is good enough is really what you're asking, right? The answer is mostly in the cost equations that I was showing earlier. But it's partly in regression evals versus capability evals. If you have a suite of 100 regressions and 1 capability eval, then you're going to be spending an enormous amount of money doing regression testing, and it's probably the case that you don't need all 100 of those regression evals. You can throw 80% of them out and still have a representative sample of regression evals. The one where you don't want to skip, where you don't want to skimp on cost, is the capability eval. So you can downgrade, you can shrink, you can compress your regression evals, and your capability eval is where you probably want to push the boat out in terms of cost. You're like, let's not care about what model we're using. Let's make this as expensive as possible, because that is where the agent is actually getting better.
Okay, thank you. And on live traces, you run both regression and capability eval, or just regression?
On live traces, there's no point in running your capability eval because it's not changing. Yeah.
You can cut cost here as well.
Yeah.
Okay, thank you.
I have no idea.
Yeah, just a question on like your actionability template, your custom eval. So like,
Sorry, can you speak up?
yeah, sorry. So a question on like the way you've defined your custom LLM-as-judge.
Yeah.
So in your example, you kind of have basically 8 separate things. So here's 4 actionable things, here's 4 non-actionables. And that's all being run as one yes or no. There's some advice online from other people that would say, oh no, you should split that up into 8 separate single checks. So like then you get a score between 0 and 8, basically.
Right.
And you're running each of those single checks one time as a separate LLM-as-judge. Do you think that's the right way to go, or do you think kind of bundling them a bit more is fine?
It's a very good question because it's a very, it's kind of arbitrary, right? It's like, what I was trying to measure there, like this is where you have to get your non-technical stakeholders involved. Like, what are we trying to measure? We're trying to measure actionability. Are we trying to measure specifically whether or not it mentioned price-earnings ratios? If that is a specific thing that the stakeholder says is important and I need to see that every single time, then you should have an eval about that. If the specific thing you're looking for is a buy, sell, hold recommendation, which is what I said I was looking for, then a PE ratio is going to help the agent get there, but it's not the thing I'm looking for. So it absolutely is context dependent and based on what your stakeholders say is the thing that is the actual definition of correct, as opposed to a contributor to correct, if you see what I mean.
Sometimes it's unavoidable, like it's kind of an either or, as long as it does one of these things.
Exactly.
Cheers.
There was another question back there.
Thank you for the talk. It was really good. I have two questions. The first question is, it seems like there are a lot of deterministic factors in the whole evals pipeline. Like, for example, if we have this result, what does it mean? Like, does it mean like the agent prompt is bad, or does it mean the rubric we provide is bad, or does it mean like if there's a human annotation, maybe the human themselves is not reliable? Do you think it makes sense to go through like phases? Like first you make sure this is reliable, then we go to the next phase, which is to compare, I don't know, whatever.
Yeah, absolutely. That's one of the reasons that I recommend building your evals iteratively. Like start with the code eval and make sure that the code eval works all the time. Then build your first LLM as a judge and make sure that one is running the way that you want it to. If you introduce multiple evals at the same time, then you're going to have the same multi-prompt problem that you had before. Like your prompt change is going to start changing multiple evals simultaneously, which is not what you want to do. That's why you want one capability eval that you're trying to hill climb at a time, while you've got existing trusted evals as regression evals that you're expecting not to change.
Thank you. And the second question is like, you also mentioned a lot of version, the rubric version or the agent prompt version or something, but my question will be, for example, when we change the criteria and do we need to run the whole evals against the new rubrics again? Maybe we have like 500 I don't know, data in the data set, then do we need to run all of this again? Or would they consider as also part of this data set, like file example, I don't know, we can use later? That's an excellent question. That is what experiments are for. Experiments give you a smaller set that you can test against, your set of failures that you can test against and say, am I getting better at this? So experiments allow you to use a small set and rapidly hill climb. Once you believe that you've climbed to the top of the hill, or you're hitting diminishing marginal returns on your hill climb, you should then go back and run against the entire data set to make sure that you haven't accidentally overfit or produced a regression that runs against the entire data set. So you don't need to run, that's what experiments are for. You don't need to run against your entire corpus every single time you make a change. But you should do it periodically when you think that you've reached a stopping point or you're about to ship. Thank you so much.
There's one more in the back, and then I think we're out of time.
Thank you, super informative. As someone who's worked in ML and deep learning research in the past, I thought that the idea of doing closed loop optimization seems really exciting, and I think it's one prospect I'm excited about in particular, but I've used things like DSPy in the past, and I think, I don't know if it's exactly helpful, but I think Andrei Karpathy's auto research idea is also somewhat related, but I haven't found anything to be particularly amazing beyond getting me to a certain threshold where it's working okay, and then I take it manually and tweak it from there. Mm-hmm. I don't know, do you have any thoughts on where that space is headed, or if there's particular work that seems promising or interesting to you?
Come to AIE World's Fair. We are hoping to present something there where we've actually made that work. But no, the answer is it's very much the frontier right now. The closed loop, autonomous, self-improving software is something we can see on the horizon. We think it's the agent, maybe when they release Mythos, suddenly it will automatically work. But it is very difficult to get to work right now, which is one of the reasons I didn't present it today, because it's kind of loose right now.
Got it. Thank you.
All right. Thank you so much for sticking around.
Thank you.